This is the first video covering the material in Chapter 5. In Chapter 5, we're going to extend our discussion of probability theory to a discussion of random variables. There are two types of random variables: discrete random variables and continuous random variables. In this chapter, we're going to discuss discrete random variables. Discrete random variables are variables that can take on only specific values within an infinite sequence or a finite number of values. That is, as opposed to continuous random variables, which can take on any value within an interval or a series of intervals. So examples of discrete random variables would be variables like gender, or perhaps the number of people who show up to a store window within a particular period of time, etc. There are many different types of discrete random variables. We don't have time to cover all of them. Your textbook covers the Poisson probability distribution, where you're looking at counts which can only take on discrete values. It's a very important distribution in econometrics and statistics, but we're not going to have time to cover it, so we're not going to cover the Poisson probability distribution in this course just because of the limited amount of time that we have. We are, however, going to focus on what I think is probably the most important discrete probability distribution, which is called the binomial probability distribution. For this probability distribution, we're going to talk about both the expected value of the mean and the variance. Before we get to talking about the binomial probability distribution, which I'm going to save for the second video in this chapter, we're going to talk about probability distributions for discrete random variables that are expressed in the form of a table. It's very illustrative, and it actually ties into frequency distributions, which we have already talked about. Basically, we're going to look at frequency distributions for discrete random variables where the frequency distribution is constructed for every single possible value that the discrete random variable can take on. And we're simply going to relabel the frequency distribution, and we're going to call it instead the probability function. We'll also talk about the cumulative probability function, and oftentimes, or I believe in your textbook, this approach is what they call the empirical discrete probability distribution, because often it will be constructed based on sampling a large amount of data. So random variables in general. A random variable is a numeric description of the outcome of an experiment. So here we're talking about discrete random variables. We'll go through a couple of different examples. But if we have a discrete random variable such as gender, male or female, we will want to code it numerically before we treat it as a random variable. For example, we could code it such as 0 is male and 1 indicates female. So a discrete random variable can assume either a finite number of values, as I mentioned, or an infinite sequence of values, such as counts. A continuous random variable, as I mentioned, may assume any numerical value in an interval or a collection of intervals. I'll give you one more example of a discrete random variable that I have used in my own research. I once published a study that looked at the determinants of patent counts within industries. So the patent count for an industry was a whole number. It could take on a value of 1, 2, 3, etc. So it was an example of a discrete random variable that could take on a number of values within an infinite sequence, since the upper limit is potentially of the number of patents is essentially undefined. For a continuous random variable, we can think of things like age, if we measure age perhaps to the nearest day, or we could think about a continuous random variable such as height or weight. Height, weight, age, those types of factors can take on any value within an interval. The probability distribution for a random variable describes how the probabilities are distributed over the possible values of the random variable. Again, if this sounds like a frequency table, then you're on the right track, because essentially what we're going to do is we're going to take a discrete variable, or before what we called a categorical value. We're going to assign a numerical value to each one of the classes that the categorical value can take on. And then we're going to construct a frequency distribution, or a frequency table, and we're going to call that frequency table, that frequency distribution, the probability distribution for that variable. We can describe a discrete probability distribution with either a table, a graph, or a formula. When we talk about discrete random variables, empirical probability distributions, we're not talking about the type of random variable that can be described with a formula yet. The first case of a distribution for a variable that can be described with a formula that we're going to cover in this class is going to be the binomial distribution. So in this slideshow, we're going to focus on tables and graphs. There are two types of discrete probability distributions here then. The first type will use rules of assigning probabilities to experimental outcomes to determine the probabilities for each value of a random variable. And the second type uses special mathematical formulas to compute the probabilities for each value of a random variable. So here we're using sort of experimental outcomes, which is why a textbook calls this the empirical discrete probability distribution. This first type is the type that doesn't rely on mathematical formulas to describe the probability function. The second type, like the binomial distribution that we'll cover in the next video lecture, that second type uses mathematical formulas in order to describe the probability function in all of its various moments. The probability distribution is defined by a probability function, and that probability function is what we denote typically as lowercase f of x. And it provides the probability for each value of the random variable. Now here we're talking about a discrete random variable, so we can actually talk about the probability that the variable takes on a particular value. The required conditions for assigning discrete probabilities will come as no surprise to you. First of all, the probability has to be greater than or equal to 0 for each value of x. And the sum of all the different values of f of x must sum to 100%. These are perfectly consistent with the rules for assigning probability that we discussed in the previous chapter. They're expressed a little bit differently here, but you will note that if the sum of all the different probabilities equals 1 across all the different values that the variable x can take on, and f of x, each one of those probabilities is greater than or equal to 0, then it's also implied that the probabilities for each one of the values of x that x can take on must of course be less than 1, or less than or equal to 1. So these are the same conditions that we've seen before. Let's go back to our very simple but illustrative example where we toss a coin 2 times. What we're going to do, if you recall, we had a sample space, and that sample space was that we could end up with a heads and a heads, a heads and a tails and a heads, and a tails and a tails. There were 4 possible outcomes. We also decided that each one of those outcomes had the same probability of occurring, basically a 1/4 chance of each one, or 0.25. And when we added up 0.25 plus 0.25, 0.25, and then 0.25 for tails, tails, we came up with a total probability of 1. Over that sample space, I'm going to define a random variable. I'm going to define a random variable as x equals the number of heads in the experiment, the number of times heads turns up in the experiment. How many possibilities are there? Well, if I roll heads and heads, then I have 2 heads that have shown up. If I roll a heads and then a tails, there's 1 heads that shows up. If I roll a tail and then the heads, right? That's also an outcome of one heads turning up. And if I roll tails and tails, the value of my variable x takes on a value of 0. Should be clear to you then that the probability of x being equal to 2 is equal to 25%. Since the probability of heads, as we know, is equal to 25%. The probability of having x being equal to 1 is going to be 0.25 plus the 0.25. You need to add up the probability of both of these occurrences, and each one occurs with a chance of 0.25. So the probability that x takes on a value of 1 is going to be equal to 0.25 plus 0.25, or 0.5, 50%. Okay. And then the probability, of course, that x takes on a value that is equal to 0 when we roll a tails and a tails, that happens, of course, with a 25% probability. So here we've expressed the frequency table for x. X can take on a value of 0 in the case of tails, tails, and take on a value of 1 in the case of heads, tails, or tails, heads. And it can take on the value of 2 in that outcome where we roll heads twice. So the probabilities then must be equal to 0.25, 0.5, and then 0.25 again. And of course, if I add all of those numbers up, it's not surprising that I get an answer of 1, or 100%. We can also talk about the cumulative probability function, and we denote that with a capital F. Just like the cumulative frequency distribution, there's no difference here. We start out with 0.25. So the probability that x takes on a value of 0 or less, and it's impossible to have less than 0, is 0.25. The probability that x takes on a value less than or equal to 1, in other words, the cumulative probability that x takes on the value of 0 or 1, is equal to the 0.25 plus the 0.5. And that, of course, is my 0.75. And then finally, with only 3 values that x can take on, the probability that x takes on a value that's equal to 2 or less, in other words, 2, 1, or 0, is going to be equal to the 0.25 plus the 0.75 plus the 0.25 for the cumulative probability of taking on a value of 2 or less, and that's 100%. There are 3 methods for assigning probabilities to random variables, as we've already mentioned: the classical method, the subjective method, and the relative frequency method. The use of the relative frequency method to develop discrete probability distributions is what your book calls, again, the empirical discrete distribution. Here's an example. Let's say that we have JSL appliances. They sell televisions. We're going to let x be equal to the number of televisions that are sold at a particular store in one day. Observing this store, we note that the number of sales of televisions can take on the values of 1, 2, 3, or 4, or they may sell no televisions whatsoever. So here are the possible discrete number of televisions that this store can sell in a day. So we count the number of TVs sold, and there's an infinite upper limit to the number of TVs that might be sold, and there's a lower limit which is equal to 0, but you can't sell 1.3 TVs or 4.8 TVs. So we have a discrete random variable. Using past data on TV sales, we come up with a tabular representation, basically a frequency distribution and a relative frequency distribution of the probability distribution for sales. So, we look at like 200 days here worth of data, and we find that on 80 out of the 200 days, we don't sell any televisions. On 50 out of the 200 days, we sell 1. On 40 out of the 200 days, we sell 2, etc. So what we're going to do is we're going to build a relative frequency distribution. And we're going to reinterpret that relative frequency distribution again as the probability function for the random variable, which the random variable is the units or number of TVs that are sold in a day. So we take these numbers, which represent the values of our random variable x, and we just recreate them here, and then we calculate the relative frequency of each one of those values for example, 80 divided by 200, that is 80 out of 200 days, saw no television sales whatsoever. And so we assigned that a probability of 0.4 or 40%. On 40% of the days, we didn't sell anything. Likewise, on 50 of the days, we sold one television. So we take the 50, we divide it by the 200, and we get our relative frequency of 0.25. So we say that the probability of selling one television in any given day is equal to 25%. We do this for every possible value that our discrete random variable can take, and when we add up all of the relative frequencies, just like we saw in Module 1, we get an answer of 1 or 100%. It really is that simple. We can also plot this in a sort of bar graph, which would be a plot of our probability function. So here's a plot of our probability function. You can see that it looks like it's a little bit skewed to the right there. Here's a formula for the expected value, or the mean, of the random variable. This is actually a more general formula than it might appear. It's perfectly consistent with the formula for the mean that we saw in Chapter 3, and it is also perfectly consistent with the formulas that we will see when we look at discrete probability distributions and look at formulas for the mean. What we do is we take each value of x and we weight it by its probability of occurring, that is f of x. F of x, remember, is a probability function, so it gives us the probability that x takes on the value, a particular value of x. So we weight each particular value of x by its probability of occurring, and once we've weighted them, we add up all of the results across all the different possible values that x can possibly take, and we come up with the expected value of the mean. The only other thing I guess I would point out here is that we're talking about mu, which is the population mean, because these probability distributions are, in a sense, models of the distribution of the population parameter. So we're not talking about x bar here, we're talking about mu. The expected value then is a weighted average of the values that the random variable may assume, where the weights are the probabilities that we calculate using the discrete empirical probability distribution. We also have a similar formula for the variance. The variance summarizes the variability in the values of a random variable. So var x stands for the variance of our random variable x, our discrete random variable x, and like before, we have our Greek notation. None of that has changed. But the formula that we're going to use here, which is again perfectly consistent with the formula that we saw for variance in Chapter 3, is we're going to take each possible value of x, and we're going to take the mean and we're going to subtract it from it. And then we're going to square those values. If we add all of those up without squaring them, we know that they will sum to 0. So we're going to square them. And for each one of those squared deviations from the mean, we're going to weight that squared deviation by the probability that squared deviation occurs. So this is, again, an average of the squared deviations from the mean, which we know is exactly the definition of variance. So the variance is a weighted average of the squared deviations of a random variable from its mean. The weights are the probabilities. The standard deviation then is defined as the positive square root of the variance. So once again, in order to get a measure of variation that's in the same units as our variable x, simply take the square root, and that's called the standard deviation. Here's an example again from JSL Appliances. What we have here is the discrete random variable x. It can take on values from 0 to 4, that is the number of TVs that are sold in a day. We've already defined and calculated the relative frequency that's associated with each one of these sales figures. 40% of the time we don't sell any TVs, 25% of the time we expect to sell one, etc. We call this the probability function for this discrete random variable. In order to calculate the average, we simply weight each one of the values in the x column by its associated relative frequency or probability of occurrence. So 0 times 0.4 is equal, of course, to 0. 1 times 0.25 is equal to 0.25. 2 times 0.2 is equal to 0.5, etc. Once we have weighted each one of the possible values that a discrete random variable can take on by its probability of occurrence, we add them all up. 0.25 plus 0.4 plus 0.15 plus 0.4 gives us 1.2. So the expected number of TVs that would be sold would be 1.2. Notice that even though it's a discrete random variable, the expected value of the mean need not be discrete. In fact, it's continuous. In this case, it's equal to 1.2. It's neither equal to 1 nor 2. Here's an example of calculating the variance for JSL appliances. Again, there are a lot of steps here. Fortunately, most computer packages like Excel will calculate this by typing in just one simple formula. But again, we have x and the values that it can take on. That's our random variable. Here, I take the difference between each one of those x values and the mean, 1.2, which we calculated in the previous slide. I take each one of those deviations and I square it in order to calculate my variance. So each one of those values that's in column 2 is squared, and that produces column 3. Minus 1.2 squared is 1.44, etc. I take each one of these squared deviations and I weight it by the probability of it occurring. And that shows up here as the relative frequency, or our probability function. So I take the 1.44, for example, and multiply it by 0.4, and I get 0.576. Once I have done that for every one of the values of the squared deviation from the mean, based on all the different values that my discrete random variable can assume, I get the last column in the table, and I add all of them up, and that gives me the variance. So the variance of televisions sold is equal to 1.66. But remember that that's in TVs squared. So in order to measure the standard deviation, which will be in terms of TVs, I take the square root of 1.66. The square root of 1.66 is 1.288, and that is the standard deviation of my random variable x, the number of TVs that are sold in a day. I would like you now to open the PDF file, Chapter 5 Worksheet for Video Lecture Checkpoints. You're going to work on a case study to answer the following 2 checkpoint questions to make sure that you're keeping up with the lecture material. This PDF worksheet will be useful not just in this lecture, but also there will be questions from it that you will want to answer in video 2 for Chapter 5.